Assalamualaikum. We greatly appreciate the critical and industry and mathematics session that I would like to share with Kathleen has that with our disability. Your teacher, thank you so very much for joining us today. My name is Seth Antapisma, and I am the moderator for today. Before we start, let's start with a starting. Tidak further ado, please allow me to welcome Dr. Nurkhairany Amyra Mokhtar as the first speaker. Dr. Nurkhairany Amyra Mokhtar from UITL in May 2020 as a senior lecturer statistic. She graduated proficiency in statistics for University of Nematova, Malaysia in 2019. She obtained her master's in science statistics from University of National Malaysia in 2016 and her bachelor of statistics from University of Malaya in 2013. Before joining UITL, she was a lecturer at UCSI University. Welcome, Dr. Nurkhairany, who will speak for 10 minutes on her research topic, Implicit relationship model for secular variables with non-news distribution, followed by a 10-minute question and answer session. In our computer, making round of applause by clicking the clap emoji.
Assalamualaikum everyone and good afternoon. Okay, my name is Nurkhairany Amyra binti Mokhtar and I would like to present to you about a research on a replicated linear functional relationship model for circular variables with the von Mises distribution. Okay, this is the team members. Okay, my team members, Prof. Dr. Yongzulina Zubairi, Prof. Dr. Abdul Ghafur Hussein, and also Dr. Nur Hafizah Muslim. Okay, so my presentation consists of the background, literature review, the problem statement, the objective, the research methodology, the results, and also the conclusion and the list of references. Okay, so let's look at the background of circular statistic. Okay, in a circular statistic, the data are measured in the range from 0 degree to 360 degrees, or in the form of radians, it is from 0 radian to 2 pi radians. Okay, it is different from the linear data. Linear data, it is from 0 until infinity, right? So this is circular data. In circular statistic, we cannot use formal analysis, okay, with the usual statistical technique. Okay, if we look here, we have the figure 1. It is an example of a graphical presentation of circular data. It is in a rows diagram. If to the linear data, we present it in histogram, but then the circular data, we present it in a rows diagram. Okay, this is the rows diagram, an example of rows diagram. Okay, there are some examples of circular data. Okay, for instance, in image analysis, the circular data occurs as planar orientation fields to represent the orientation of ridge on our fingerprints. Okay, in medical application, Jamala Madaka et al. Discuss about the angle of knee flexion to assess the recovery of the orthopedic patients. Okay. The example in biology, Karif built a time series model for circular data with application to the protein conformational angles. And then in geology, the geologists studied the direction of the Earth's magnetic pole. And then in meteorology, an example here, Masran and Razali identified the most dominant wind direction in Malaysia during monsoon season in 2007 to 2009. Okay, that is an example, some examples of circular data. Okay, now we would like to look for the error invariable models. Okay, it is something different from regression model. Okay, EIVM, error invariables model. Okay, they are the models that account for the measurement errors for both X and Y variables. Okay, the ordinary regression, we only consider the error term for the Y variable, right? But then in EIVM, okay, we measure the error terms for the X and Y variables. And then we have three types of EIVM. Okay, first is the functional EIVM. It is when X is assumed to be fixed. And then we have the structural EIVM. It is when X is assumed to be random. And then there are ultra structural EIVM. Okay, it is when the model is synthesis between the linear and also structural EIVM. And then the focus of this topic, it is on the functional EIVM where X is assumed to be fixed. Okay, there are some development of EIVM for circular variables. Okay, for instance, in 1997, Hussein proposed the unreplicated linear functional relationship model with the presence of slope parameter. In 1998, Hussein developed the unreplicated complex linear functional relationship model for circular variables by extending complex linear regression model. And then in 2003, Carriers and Wyatt, okay, they developed a model which proposed the parameter in connection with the desired symmetry of the functional relationship model. And then in 2009, Hassan et al. Extended Hussein model to be simultaneous functional relationship model, okay, with the presence of the slope parameter. Okay, and then let's look at the development of the replicated model. Okay, in 1970, Barnett proposed a functional relationship model with replicates observation for linear data. Okay, and then in 1972, Dolby and Lipton proposed a non-linear functional relationship model with replicated observation and correlated errors. And then in 1979, Chan and Mark proposed a linear structural relationship model with replicated observation for linear data. And then in 2005, Hussein proposed a functional relationship model with replicated circular observations with the slope parameter. Okay, so, okay, this is the problem statement. Okay, Mokhtar 2016 and 2019 has studied the parameter estimation for the case of equal error concentration in unreplicated linear functional relationship model by using the approximation by Fisher 2003. And then the concentration parameters in linear functional relationship model may only be estimated if the ratio concentration is known. Okay, there may be the case where the ratio is not known, and therefore this study proposes a new model that is called as replicated LFRM, in which in order to estimate the parameters, the ratio is no longer necessary. Okay, so before we start, we have to do some comprehensive study on circular statistic and also the LFRM. And then we need to do some study on the parameter estimation of the unreplicated LFRM for circular data, in which the derivation of the parameter estimation is done using the maximum likelihood method and the Bessel function. And then we derive the covariance matrix by using the Fisher information matrix. And then we do the simulation study and the application on real data set. And then we develop the model to become a replicated LFRM model for circular data. Okay, replication is done using the pseudo-replicate method. And then we do the derivation on the parameter estimation using the maximum likelihood method and the Bessel function. And then we do the derivation on the covariance matrix using the Fisher information, and we carry out a simulation study and applied it to the real data set. Okay, so what is linear functional relationship model for circular data? Okay, y equals to alpha plus beta x modulo 2 pi. Okay, in equation number 1 is the unreplicated linear functional relationship model. Okay, in 2003, Carriers and Wyatt, okay, they acute the beta to becomes 1 so that the model becomes symmetry. Okay, we can have this one as the model, and alpha is the rotation parameter. Okay, the small x and small y are subject to random errors, delta I and epsilon I respectively. Okay, this is, okay, the small xi is equals to the big xi plus delta I. Okay, delta I is the error. It is distributed with the von Mises distribution with the mean of 0 and the concentration parameter is equals to kappa. And then the small yi, it is equals to the big yi plus the epsilon I. Okay, the epsilon I is the error terms. It is distributed with the von Mises distribution, okay, with the mean equals to 0 and the concentration parameter equals to nu. Okay, this is the parameter estimation for the Carriers and Wyatt model. Okay, number 2 is the model, and then this is the PDF of the von Mises distribution. It is given in equation number 3. And then we have the log likelihood function of the von Mises distribution for the unreplicated data. It is given in equation number 4. And then the parameters can only be estimated with the presence of the ratio concentration parameter, that is lambda is equals to nu over kappa. Okay, so we need to have this in order to have the parameter estimates for the unreplicated linear functional relationship model. Okay, so now our model is to propose a new replicated LFRM for circular data together with its parameter estimation and also the covariance matrix. Okay, so the replicated model, okay, this is the model, okay, but then the difference here is that we have the corresponding pair of xi, yi. Okay, there may be replicated observations of xi, yi occurring in P groups. Okay, so now the variable of x consists of xij. Okay, just now was just xi, now we have xij. Okay, okay, this is made on xi. Okay, so now the error terms becomes the delta ij. Okay, it is distributed with the von Mises distribution. Okay, with mean is equals to 0 and concentration parameter equals to kappa. And then for the y variables, okay, we make it replicated. Okay, it becomes yik. Okay, and then the error terms also becomes the epsilon ik, okay, distributed with the von Mises distribution, which means equals to 0 and the concentration parameter equals to nu. Okay, and then for the parameter estimation, again, we have the von Mises distribution. Okay, and now the likelihood function of the von Mises distribution for the replicated data is now becomes the equation number 5. Okay, we have n and m here, and also our x and y becomes xij and also the yik respectively. Okay, so to obtain the parameter estimation, we use the method of maximum likelihood. Okay, we have the partial derivative. Okay, del log L. Okay, and then we make it equals to 0. And then we obtain the alpha hat like in the equation number 6. And then we obtain the maximum likelihood estimator of xi. Okay. Okay, we have the partial derivative of log L with respect to xi. We make it equals to 0. Okay, xi may be solved iteratively by some initial guess. Okay, suppose we have xi naught, okay, is an initial estimate of xi hat. Okay, then we have this equation. Okay, and then we have the partial derivative equation becomes, okay, this equation, okay, sine plus sine something plus sine something equals to 0. Okay, this is the equation. And then for the small increment, and then the cos of the increment I is approximate equals to 1. And then the sine of increment I is approximate to the increment itself. And hence the equation is simplified to become the equation number 7 as the maximum likelihood estimator of xi. Okay. And then we have the maximum likelihood estimator for kappa. Okay, first we need to have the partial derivative of log L with respect to kappa equals to 0. And then, okay, the kappa hat here can be obtained by using the approximation given by Fisher, 1993. Okay, where in S plus it has been simplified by using the function of A inverse. And then we may have the equation number 8 as the maximum likelihood estimator of kappa hat. Okay, and then for the maximum likelihood estimator of mu, okay, we have the partial derivative of log L with respect to mu. We make it equals to 0. And then we obtain the equation of the maximum likelihood estimator of mu. Okay, we have mu hat. It is like in the equation number 9. Okay, and then to derive the covariance matrix for the replicated LFRM, we have the partial derivative of log L with respect to alpha, xi, kappa, and also nu respectively. Okay, we obtain each of them. And then we need to have the second derivative. Okay, and then we have the expected value of the negative, okay, the negative second derivative. And then we obtain equation B, equation E, okay, and then we obtain D, C, okay, and then by using the Fisher information matrix, okay, we plug in the equations, okay, we have B, E transpose, and also D, okay, and then we have the covariance matrix of kappa hat, nu hat, and also the alpha hat. Okay, we obtain the covariance matrix of the parameter estimates as given in the equation number 10. Okay, whereas the variance of kappa is given in the equation number 11. The variance of nu hat is given in the equation number 12. And the variance of alpha hat, it is given in the equation number 13. Okay, then, okay, how to know whether the derived method is reliable? We use the simulation study. Okay, it is a Monte Carlo simulation study for the replicated LFRM. The programming for the simulation study for the replicated LFRM, we use the replication is equals to 5,000. Okay, we use the S plus. We would like to test the biasness of the parameters. Okay, before we establish the model, we have to test the biasness of the parameters. Okay, step 1. Okay, how to arrange the data. Step 1, all data of X and Y variables, they are divided into P groups, okay, with M elements such that P times M is equals to N. Okay, we have step 1, all the data of X and Y variables are divided into P groups with M elements such that P times M is equals to N, where P is the maximum divisor of N and P is less than or equals to M. And then step 2, the data are then arranged in the form of P times M matrix. And then step 3, the parameter estimation is done by using the proposed method. Okay, and then in step 4, we repeat, okay, step 1 until 3 for 5,000 simulations. And then step 5, the biasness of each of the proposed parameter estimation for 5,000 simulations is measured by using some measures. Okay, it is given in the following pages. Okay, this in this table, okay, it is an example here. Okay, some examples, sample size 50, and then we divide the subgroups and also the number of elements. Okay, and then, okay, these are the measures of the accuracy. Okay, the measure of the biasness for alpha hat. We use the circular mean. Okay, and then we have the circular distance here, and also the mean resultant line here. Okay, and then we have the measures for the accuracy of kappa hat. We calculate the mean of kappa hat. Okay, we estimate the bias, and then we calculate the estimated root mean square errors. And then we measure the accuracy of nu hat. Okay, we calculate the mean of nu hat, and then the estimate bias of nu hat, and also the estimated root mean square error, ERMSE. Okay, and after that, okay, this is table 1 is the results of the simulation. Okay, the circular mean of alpha hat becomes closer to the real value. We have to set the real value, one real value, where the real alpha is equals to pi over 4, okay, which is 0.7854. Okay, we can see here, okay, as the sample size increases, okay, the circular mean becomes closer to the real value. Okay, and then there is a small circular distance, which suggests a good estimation of alpha. You can see here, okay, it becomes very, very, very close to 0. And then for the mean resultant length here, it becomes closer to 1 when n and the concentration parameter increase, okay, where this suggests a good accuracy of alpha hat. Okay, and then the result for kappa hat, okay, from table 2, okay, you see here the mean of the kappa hat. Okay, it becomes closer to their true value as the kappa and the sample size increase. Okay, this is the true value for kappa. As the n increases, okay, the mean increase. The mean becomes closer to the real value. Okay, you see here, you can see from the table. And then the estimate bias decrease when n increases. Okay, there is a good estimation for kappa, in particular for large sample size. You can see it becomes very close to 0. And then the ERMSE has decreased with the increasing value of n, and this suggests that kappa hat is a good estimate of kappa. Okay, same thing goes to the nu hat. Okay, in table 3, you can see that the mean of nu hat becomes closer to the true value of nu as the sample size of n increase. Okay, and then there is a good estimation for nu, in particular for large sample size, as the estimate bias decrease when n increases. Okay, and then for the ERMSE, we can see that the value decreases with the increasing value of sample size, and this suggests that nu hat is a good estimator for nu. Okay, then this is the application. Okay, we would like to apply this model. Okay, we apply this model by using the wind direction data taken from Alostar Coastal Station during the southwest monsoon period, which is from August to September, but at 2 different years, namely 2016 and also 2017. Okay, the variable X is the wind direction in 2016, and the variable Y is the wind direction data in 2017. Okay, so this is the Rose diagram, okay, for 2016, and this is the Rose diagram in 2017. Okay, there are 2 different data. Okay, this one is the summary statistic. Okay, this table. Okay, and then when we apply the model, we feed the data with the replicated linear functional relationship model, and the model is given by y hat is equals to 6.15384 plus x hat modulo 2 pi, and then the values of the parameter estimates and their variances are given in the table 4. Okay, we can see the variance is 0 point something. Okay, the value of the estimation of the error concentration of x and y are 4.68439 and 2.69337 respectively. Okay, it shows that the random error of wind direction data of Alostar in 2016 is more concentrated to be compared to 2017. And the parameter estimation in the proposed replicated LFRM is consistent with the earlier univariate analysis. Okay, so if we compare here, okay, if we compare here, we can say 2016 is more concentrated. Okay, this one, 2016 is more concentrated than 2017. So it is consistent, okay, with the real data. Okay, in conclusion, okay, unlike the unreplicated LFRM, the novelty of this replicated LFRM is that the maximum likelihood method may directly estimate the concentration parameters without having to make any assumption on the ratio of the concentration parameter of lambda. Okay, and then another advantage of this model is that we no longer need the concentration factor in estimating the error concentration parameters as mentioned by Keris and Wyatt. Okay, and then from the simulation study, the biasness of the estimation is small, and that indicates the adequacy of the proposed model. And the model is illustrated by the wind direction data from Alosta Coastal Station for 2 different years, okay, during southwest monsoon. Okay, there are some further works that may be done. Okay, this study may be further extended. The further works could be on the development of the replicated LFRM for unbalanced observation. Just now was the balanced observation. Okay, another replicated model may be extended to a model that incorporates linear and circular variables. Okay, the model just now was for circular variables and circular variables. Okay, maybe we can develop a new model for linear plus circular variables. This model may be applied to incorporate the wind speed and wind direction data for the replicated observation, and also a simultaneous replicated LFRM for circular variables may be developed, and the studies on outlier detection and missing values may be discussed for new models mentioned above. Okay, this work actually is already published in Web of Science journal in Science Malaysiana. Okay, it is already published before this. Okay, and then this is the list of reference. Okay, I think that's it from me, and with that, thank you.
Thank you for sharing your interesting and Nurkhairany. Now we will ask our question and answer session. Please feel free to share your question or give opinion.
Hello. May I have a few questions, please?
Yes.
Couldn't you please clarify a few things which I just presented here? First of all, regarding your circular data in the first slides, but the latest one is 2003 or 2005, as I remember. Right? Why too old?
Oh, okay. Actually, okay, this one is it?
The same, yeah, the same with literature review.
Yeah, yeah.
The last one is 2009. So there is a gap until 2016. No research was done between 2009 and 2016.
Okay, this is just the development of EIVM for circular variables. We may have some additions here. Okay, between 2009 and 2023. Okay, we may add more actually.
Okay, how about your applications? Because also 2005 is the latest one.
Yes. Okay. Okay. This one. There are limited researchers. Okay, who did the replication of the models. Okay, the latest one of 2005, and then we may have in 2022, if I'm not mistaken. Okay, that is my friend. Okay,
why so?
I forgot to add here.
So long gap.
Oh, based on our
Long gap.
research, because the maybe it's because of this topic is
Not
less.
interesting.
But then this topic is
Maybe so. Maybe the case, maybe the topic is not interesting. So there's people don't interested in it. This topic.
I'm not
Do you
sure.
think?
Okay. We go to the place the place that is less people are interested.
Nice, okay. All right. So next question is related to your slides 15, 14, 15. There are some parameters there, M and P and so on.
This one?
Next, I think. I guess next.
This one?
Oh, yeah.
Okay.
Because your estimation, your estimations, errors depends on that parameters, right? M, N, and so on. What's the correlation between them? Because optimization, in terms of optimization, maybe in some values of M, N, or relation between them, you will get a more optimal case of estimation and errors.
Okay, this is the unreplicated model. Okay, we extend the model. Okay, we extend the model so that we don't need to have the presence of the ratio concentration parameter. So that is the contribution of the replicated model.
But still, your estimations and the errors depends on that n, right? You have the summation. The limit of summation is n. Somewhere you use m. So that m and the n, this notes, you see, are here.
Okay.
M, you have M, N, J, K, and so on.
Yeah.
Your estimations and the errors depends on that parameters, right? If you take large one, maybe you will get more less error or good estimation and so on. Do we have such kind optimization?
Optimization. Okay, maybe we can explore optimization afterwards. Okay. This is this is the new log likelihood for the replicated data, for the replicated model. Okay, in which for the unreplicated model, for the unreplicated model, we don't have the big M and the big N just now. Okay, and then it is slightly different. It is slightly different from the replicated and the unreplicated.
Okay. One more thing on your mod 2 pi.
Mod 2 pi?
Just,
okay.
Is it just if you have some result on real line, convert it to mod 2 pi by using polar coordinate system.
Polar coordinate system?
Yeah.
How is it?
No, because you have Cartesian coordinate system and the polar coordinate system. So you have a relation between them. Just you have some result on Cartesian coordinate system, then you can convert it to polar coordinate system by using polar transactions. Why not?
Okay.
You're putting here mod 2 pi. Is it related to that or research method or methodology is totally different?
Okay, this one, why we have mod 2 pi, okay, the angle, okay, the angle in degree, we have to change it in the form of radian. Okay, that is why we have the mod 2 pi. Okay, it is angular. Okay, originally it is angular. We got the data, for instance, from the meteorology data. Meteorology department. And then the data given to us in degree, it is in angle. And then we convert it to become radians. Okay, it can be from 0 until 2 pi radians. And that is why we have the modulo 2 pi here.
No, that is a relation between Cartesian and the polar coordinate system. In Cartesian XY, in polar coordinate system, you have rho and angle. So just convert that what we have in Cartesian system to polar system by using that relationship between that two coordinate systems. Is it? Is it true?
Yeah, to become the polar coordinate system.
Okay, thank you.
Okay, thank you for the feedback. Any more questions? Okay, I think there is no more questions. With that, I would like to thank everyone, and I would like to thank KPPIM, UiTM Shah Alam for the opportunities for presenting this work. Thank you so much.
Thank you, Dr. Nurkhairany, and the presentation. So I will continue. Let us now go on to our second speaker, Dr. Nematova Eminovna. In 2022, Dr. Nematova Eminovna has been a senior lecturer at National University of Uzbekistan. She received her PhD in computational mathematics from the National University of Uzbekistan, as well as her master's degree in cryptography and cryptanalysis from the same institution. Second, Dr. Nematova Eminovna, who will give a talk entitled Implicit Upwind difference scheme for a hyperbolic system of two equations with variable coefficients and a lower term for 30 minutes, followed by a 10-minute session and answer session. Please put the flag emoji to give our second speaker a healthy round of applause. Please, Dr. Nematova.
Assalamualaikum. Good afternoon.
Walaikum salam.
Myself, this implicit Upwind difference scheme for a hyperbolic system of two equations with variable coefficients and lower terms. My full name is Nematova Dilfuza Eminovna. Slide title: first, abstract problem statement and preliminaries. Implicit Upwind difference scheme. Conclusion. Reference. This abstract. In this work, the exponential stability of an Upwind implicit difference scheme for a mixed problem posed for linear symmetric hyperbolic systems of two equations with disparity boundary conditions is provided. The case is considered when the coefficients of a linear symmetric hyperbolic system are variable and the lower terms are involved in the system. For the solution of the initial boundary difference problem, an explicit discrete quadratic Lyapunov function is constructed. A condition for the boundary conditions is found under which the exponential stability of the implicit Upwind difference scheme for the mixed problem for linear symmetric hyperbolic systems with disparity boundary conditions in the L2 norm is provided. Problem statement and preliminaries. Let us consider the case when the characteristic velocities depend on the spatial coordinates. Consider a linear symmetric hyperbolic system, one equation. system equation. Here A1, A2 are given positive functions. Q1, Qx are given functions such that our tasks is to analyze the exponential stability of the implicit difference scheme for the numerical solution of system with linear boundary condition in the canonical form for x equals 0, 2 boundary conditions, and at x equals L, 3 boundary conditions. V2 equals times V1 plus C2. And with initial data V1 x0, VRS are real parameters and belong to C0. Assume that the components of the initial data function vector satisfy the compatibility conditions. 5. Implicit Upwind difference scheme in domain G. We construct a difference grid with steps delta x in the x direction and delta t in the t direction. The nodal points of the difference grid are denoted by tkxg. The set of nodal points of the difference grid is denoted by gh. The values of the numerical solution as the nodal points are denoted by VEJK. The steps of the difference grid delta x, delta t are chosen in such a YZ equations. G times delta x equals L we meet to find a numerical solution to the mixed problem. One symmetric hyperbolic system, boundary conditions, initial conditions, compatibility condition, our reference grid GH. We propose the following difference scheme for the splitting in directions. The original system is approximated by the implicit scheme. V1 for this equation, V2 for this difference scheme. The exact value of the initial functions are the nodal points of the initial layer in time is taken as the initial data. To approximate boundary conditions 2, we take values V2 from V2 0 chi plus 1 as equal to 0 values at net boarding point V1 1 chi plus 1. Boundary conditions 3, in the same way we assume the values grid functions V1 capital G chi plus 1 to be equal to V1 and G minus 1 chi plus 1. In this case, it is obvious that the approximation of the boundary conditions has the first order accuracy. We study the Lyapunov stability of the initial boundary difference problem from 6 to 8 based on the approach of constructing a discrete quadratic Lyapunov function. As a candidate for a discrete quadratic Lyapunov function, we propose the following function. L1k this equation here, L2k this equation, E1j this, A2j this equation. Here mu1, mu2 are positive constants to be determined. Definition 1, the solution to the initial boundary difference problem from 6 to 8 is scaled Lyapunov stable if there are such positive constants alpha and beta, z for any initial vector of function phi1j. Solution of initial boundary difference problem from 6 to 8 satisfies the following inequality. Here L2 is discrete space L2 and presents a family of sequence of grid vector functions of the form such that Theorem 1, let capital T positive and the discrete Lyapunov function be defined using formula Lyapunov function. If matrices are S of the parameter of boundary conditions as SR, boundary conditions parameter, obey inequalities, absolute R times S, absolute less than 1, dissipative conditions of the boundary conditions, then numerical solutions VJK of the difference initial boundary value problem from 2 8 the Lyapunov stable. In this sense of definition 1. Lemma 1 of the prove some lemmas, prove theorem some lemmas. Lemma 1 on the solutions of the first and second equations of the difference scheme 6 respectively the following inequalities hold. Here V1 chi plus 1 this V2 chi plus 1 this equation. 2 let I1j the current number rho 1j this for the first difference equation of same the first difference equation of then 6 takes the form. Let us denote the JK equal to this. Both parts of the first difference equation of scheme and 6 respectively are multiplied by 2 multiply V1J chi plus 1. We transform separately the first and second terms of the left side of equations, written as follows. Note that equalities 1 and 2 are provided by direct verification. Performing transforms 1 and 2 from 13 we obtain this. Then from identity 14 for the expression the JK we obtain the following relation. V J chi plus 1 this equation. There are two cases. One case Q1J greater than or equal to 0. Case 2 Q1J less than 0. Note that in the first case V1J K plus 1 greater than 0. With this fact in mind, instead of equality, we have the following inequality for the JK. Applying this inequality for the V1J chi to expression L1 k plus 1 minus L1 k divided by delta t, we obtain 15 equation. In the second case, therefore the inequality WVJ chi plus 1, considering the fact for the JK instead of equality, we have the following inequality. Applying this inequality for the JK, the 1JK to the expression, we get this equation, 16 equation. Inequalities 15 equation and 16 equation imply inequality 10. Similarly, we obtain equality 11 for L2K. When we denote current number, rho 2J, by rho 2J is the current number for the second difference equation of scheme 6. Then the second difference scheme 6 takes the following forms. We denote Zeppa 2JK equal to this. Both parts of the difference equations 17 are respectively multiplied by 2 times V2J chi plus 1. We obtained 18 equation. We transform separately the first and second terms of the left side of equations 18 as follows. First equal to this, second equal to this. Note the equalities 6, 3 and 4 are provided by direct verification. Performing transformations 3 and 4, 18 we obtain 19 equations. Then from this identity 19 for expression Zeppa 2JK obtains the following relation: V J chi plus 1. There are two cases, case 3, case 4. Case 3, Q 2J greater than or equal to 0, Q2J less than 0. Note that in case 3, W2J chi plus 1 greater than or equal to 0. Considering this fact for the 2J instead of equality, we have the following inequality. Applying this inequality for the 2JK to the expression L2 chi plus 1 minus L2 k divided by delta t, we get 20 equation. In the second case, B2J chi plus 1 equals to therefore the inequality. Considering this fact for the 2JK instead of equality, we have the following inequality. Applying this inequality for the 2JK expression, we obtain 21 equation. Inequality 21 implying equality 11. Lemma 1 is provided. Lemma 2 to reason or delta x the following two summation by parts formulas. B1 chi plus 1 equal to this. B2 chi plus 1 equal to this. Here, we first prove the summation by parts formula 5. For this purpose, we use the following differentiation formula. We will study each sum on the right side of the above equation 7 separately. It is easy to prove the following equalities. Indeed, the proof of equality A follows by direct summation. To prove equality B, we use the following chain of equalities with accuracy or delta x. Let us now prove the summation by parts formula 6. Similarly, for this, we use the following differentiation formula 8. For each sum on the right side of formula 6, we apply the following equalities respectively. C, D equations. Indeed, the proof of equality C follows by direct summation. To prove equality D, we use the following chain of equalities with accuracy delta x or delta x. lemma 2 is provided using the summation formula plus 5 and 6 from lemma 2 for the expression L 1, 2, chi plus 1 respectively, we obtain the following inequalities and 23 inequalities. Let's introduce the following notation. Here v min equals to min v1, v2. Let the functions q1, 2x satisfy the inequality v min greater than 0. Then the following lemma is true. Lemma 3, let the conditions of the theorem 1 be satisfied. Then the following inequality is true. 24 inequality. Proof using the inequalities for the quadratic forms L2k, L1k, L2k, we have here B1 chi plus B2 chi plus equal to this W chi plus 1 nu. Substituting the values of B1 chi plus 1, B2 chi plus 1 from 5 and 6 respectively into the W chi plus 1 V expression. We obtained this equation. Using the boundary conditions 8 for the W chi plus 1 new expression, we obtain this equation. W chi plus 1 nu equal to mu1 multiplied this first boundary conditions plus from first boundary condition plus mu2 times from two boundary conditions. Let's use the inequalities 8 inequality and 10 inequality. Then for the expression W chi plus 1 nu, we obtain the inequality W chi plus 1 nu less than or equal to WV1 chi plus 1 nu plus WV2 chi plus 1 nu. Here WV1 chi plus 1 nu equal to this equation. WV2 chi plus 1 nu equal to this equation. Let us separately study the expression WV1 2 chi plus 1 nu. Substituting the values E10, E21, E2j, E2j minus 1 into the expression V1 chi plus 1 nu, we get. Since according to theorem 1, the parameters R and S of the boundary conditions 8 satisfying the inequality R times S absolute less than 1, then we choose the parameter gamma nu positive in such a way that the inequality takes place. Next, we choose the parameters mu1, mu2 from the condition. Therefore, from here we easily obtain the inequalities. As a result, for the expression WV1 chi plus 1 nu, we have the inequality. This V1 chi plus 1 nu less than 0. Substituting the values A1 0, E2 1, A2j, A2j minus 1 into the expression WV2 chi plus 1 nu, we get. Let us introduce the notation mu max. Then for the expression W2 chi plus 1 nu, we get following inequality 27 inequality, taking into account inequality 26 and 27. we obtain inequality 24. Lemma 3 is provided. We represent inequality 24 as L chi plus 1 less or equal to alpha times LK plus beta, where alpha this, beta this equation, not that alpha less than 0. Let us be given a sequence of real numbers satisfying inequality 28 for alpha positive and beta positive. Then according to lemma 5, 1, a discrete version of Cronwell's lemma. 15 reference. The following inequalities holds. It should be noted that at sufficiently small delta t inequality alpha holds. Then according to the formula for the partial sum of the terms of an infinite geometric series with denominator alpha, absolute value alpha less than 1, the following equality is true. Taking into this equality from 22, we obtain the following inequality. He beta this equation. Therefore, if times s absolute value less than 1, then the solution of the initial boundary difference problem.
Excuse me, Dilfuza, your slide's not moving. Is it you're just focusing on one slide only? Because your slides are not moving. Only 22, 23 inequalities are shown.
22, 20,
not 24. Why not 24? You're talking on 24, but not 24.
Yeah, repeat 22. This 22 repeat here. Repeat it. This 22.
setting.
This 24.
Still cannot see. On screen, we see 22, 23 only. Can you scroll down? Maybe just scroll down and see. Next slide.
See.
It's not moving.
You see?
No 24.
We
22
see
in the 23 only.
Not 24 here. 25.
This me 25 inequality here in my screen.
You're not to core setting, Dilfuza?
24, yeah.
24.
In the lemma.
What? Stop.
Some problem with my computer maybe, because
Yeah,
I see only 22 and the 23. Slide with 22 and the 23 only.
I see 24 also.
And I can also see.
Some problem with your computer.
Maybe. Sorry.
Excuse me, Prof. I think the slide now at 25 page, right?
25.
The page 25.
Yeah.
No, I see two formulas, two inequalities, 22 and the 23 only. No any further slides in my computer. I don't know, maybe my computer problem.
But in our screen, it's already page 25.
Oh, I see. Okay, sorry. It's
So
okay.
I think there is no problem with the connection
All
to
right.
your laptop.
Yeah.
All right. Thank you. Sorry.
Can I continue?
Sure. Sorry.
Examples of numerical calculation: the system of difference equation from 1 to 4 was solved for the following initial data: A1, A2, Q1, Q2. This equals this, C equals this, S equals this. The condition 8 of theorem 1 on the parameters are S is also fulfilled. It follows from here that according to theorem 1, the numerical solution VGK of the difference initial boundary problem from 6 to 8 mesh is stable in the L2 norm. See below the present the graph of the L2 norm for the numerical solution relative to K, confirming the exponential stability of the numerical solution. Exact solution V1 this graph, V2 this graph, exact solution. Approximate solution V1 this graph, V2 this graph. Comparison these graphs, Conclusion: in this article we investigate an implicit upwind difference scheme for the numerical calculation of stable solutions of a one-dimensional linear symmetric hyperbolic system with disparate boundary conditions. In the case of variable coefficients and with Law's terms, a discrete analog of the Lyapunov function, we constructed an a priori estimate for it was obtained. The obtained a priori estimate allows us to assess the exponential stability of the numerical solution to the mixed problem, and this gives us the opportunity to prove the convergence of the numerical solution. The flow of electrical energy, the fluid flow in open channels, or the gas motion in pipelines, the light propagation of in optical fibers, the movement of chemical and a plug, blood flow in mammalian vessels, road traffic, and the spread of age-dependent epidemics, or chromatography are typical examples of processes that can be described by hyperbolic partial differential equations. The proposed implicit difference scheme can be used for numerical calculation of various processes described by hyperbolic systems. References this. Thank you for your attention.
Thank you very much for your sharing, Dr. Nematova. Dilfuza Eminovna. Now, we will now begin the question and answer session. Please feel free to speak up early.
Can you repeat?
Okay, Dr. Nematova, I have one question. Can you go to slide 7?
Yettinci slide kabarin Dilfuza.
7 slide tamam.
Yetti.
Okay, I just want to understand how it works on the subscript. Okay, you have equation 6, right? So I want to understand the key is from 0, 1 until what value? Is it infinitely value?
These boundary conditions 8 K
K plus 1, but your K
K
is
plus
from 0, 1 to what? Until what number?
Capital we example computational example programs capital K, but K 8 boundary conditions.
عشان يوزب قين كالتكادل أوزر
Capital K. Capital K.
Mana bukan nol bernatural tonlar mı yakın? Bütün tonlar mı katı tonlar? Natural ton mu?
Noldan boşlanadi indeksi katta K'gacha davom ettiradi.
natural sonlar 1, 2, 3 ve hokazo.
Natural sonda nol ham borda o'zi, natural son boshlanadi.
So until
Butun
capital K, uppercase K,
Capital K.
but K may be any, right? Any natural number.
Any natural number. Okay. But
No, this one,
there is no
not long.
limitation.
Not lowercase, but no, to take some summation, you should have some fixed number. K lowercase K runs 0, 1, 2 up to some capital K.
I see. Yeah. I think.
Yeah, because that K is not fixed, so that's why it's, there are dots there.
Yes.
All right, thank you.
Otherwise, it can be said that it can go to infinity, which is impossible. It has to obey some properties.
Now that is understood here. Just K is 0, 1, and up to some number K, because it cannot be infinity.
Okay.
So that is the reason.
Okay. Thank you, Prof.
All right. My question is nothing you said on previous research and literature review. Any literature review? Who done that? Which kind of research? This kind of research was done by whom previously?
كملا يشلقان
We use work my supervisor Aloyev Rahmatullah Jurevich and Khudaberganov Mirzali work paper.
4, 5, 6, 7 deb ketingda.
4, 5, 4 paper, 5 work, Aloyev, Ishkvatov, Davlatov, 6 Aloyev, Bloch and Khudaberganov, 7 Ishkvatov, 8.
No, why I'm asking this? Because to write next paper, you should have some problem in previous paper for future research. Then step by step, you should to go up. So that is the reason why every time you should to jump from paper the one, and that was considered in that problem, that case is improved or generalized, so on. You should emphasize that cases to motivate your research. It would be better to explain in that case. Okay. That is another problem. Okay, so whatever I see here, some point for collaboration with Dr. Iskandar. I think Dr. Iskandar is not around. I think this research is to Dr. Iskandar's area of research. if we have such seminar to find some collaborate, if such attempt done would be nice between UITM researchers and the National University researchers. So please, if you have chance, just contact Dr. Iskandar and discuss these kind of things with Dr. Iskandar.
Okay.
Yeah, because your supervisor, Professor Aloy, knows Prof. Prof. Zanaria. Dr. Iskandar is his student. So I think the area is close to each other. Okay, thank you.
Okay. Okay.
Can I ask some questions?
Yes.
Okay. Thank you for your presentation. And I see you applied the your proposed method to a test example. Yeah. Did you attempt to solve test example using other methods, or only just use the implicit Upwind difference scheme only? Do you get it?
Difference methods are often used to determine the numerical value of Lyapunov stable solutions of the mixed problem. In this case, either an explicit or an implicit difference scheme is usually proposed. It is well known that when explicit difference schemes use for the numerical solution of the mixed problem, then certain restrictions are imposed on the steps of the difference grid. The so-called Courant-Friedrich-Levy conditions, very often for certain hyperbolic systems, it is required to determine a numerical solution in a large time interval. And then the length of the calculation interval for special variables is very large compared to unity. For example, when the parameters of the water flow in open channels are calculated.
Okay. Thank you.
Is there any question? So if there is no question, I will pass it to the next question.
Can you repeat slowly?
If there is no question, I will pass it to the next question, which is second question.
Your voice is not clear. I cannot understand. Just maybe because of your microphone. Just off your microphone and say something.
Oh no, what I mean is, if there is no question, I will pass it to the next question, which is second question. So, can I answer to the next question? Can you hear me? Hello?
Hello.
Can you can hear me clearly, right?
I'm here.
Next, let's go on to our photo session. I sincerely hope that everyone You turn on their camera for this.
I cannot catch voice.
Can you open the camera for the photo session? Okay, we will wait for everyone to open their camera. So everyone ready? Okay, 1, 2, 3. Okay, again. Thank you. 1, 2, 3. Okay, here we will already set the picture. I will share the QR code.
Excuse me, Nur Arifatul. Excuse me, so
Yeah.
sorry. Can you write your question because we cannot catch your voice?
Oh, in the session. We already on to the next session, which is taking photo.
Okay, okay, okay.
I want to open the camera again so we can take. Dear participants, kindly fill in the attendance form to get your e-certificate and 20 hours photos for your ATM staff. You will receive an e-certificate once you fill in the attendance. If you'd like to thank speakers, Dr. Nurkhairany and Dr. Nematova, Dilfuza, and Eminovna for their enlightening insights. The final session is now over. Alhamdulillah, thanks to Allah, we have completed our 12 webinar sessions. We regret for any flaws or errors that occurred during the webinar. Thank you very much to all the participants for your support throughout the year 2023. Finally, until we meet again, let me share this quote by Bonnie Blair, a retired American speech setter. It's sad to know I'm done, but looking back, I've got a lot of great memories. Have a great weekend. Assalamualaikum.